All right, something seems to have changed, but we appear to be recording. So welcome to chapter 5.3 in our calculus book. This section is all about connecting the graphs of derivatives and second derivatives to the original function. So what I want to do is I want to start by just taking a look at some of the things on an example graph. And I've gone ahead and I scanned this out of the book rather than try to spend the time drawing it. So if you look at this, what you'll notice is all these definitions that you've seen before. We're going to have absolute minima, we're going to have absolute maxima, and then any other maximum or minimum that is found sort of somewhere on the graph, but is in between that, those absolutes, is just a local maximum or minimum. We know that maxima could be at either the derivative equals 0, horizontal tangent, or it could be undefined. So in this case, we have a corner. We also know that we've got to be a little bit careful that it is not automatic that a derivative equal to 0 gives us an extrema. There could be a plateau where the graph comes up and then flattens out and keeps going. And finally, notice the first derivative when we're talking about the value of the first derivative, or the sign, increasing, greater than 0, increasing, increasing. And then looking further, we see decreasing, less than 0, decreasing, less than 0, decreasing, less than 0. And we're really going to do a deep dive into how we find these things and some more information that we can tell about an original graph if we're, for example, given a graph of the first derivative. What can we figure out from the graph of the first derivative? And we're going to come back and we're going to be basically looking at all these scenarios on this graph if we're given the graph of that first derivative. So let's start by talking about something called the first derivative test. And the first derivative test says that if f prime changes sign at some value of x, we'll call it c, if it goes from positive to negative, then we must have a local maximum there. And we can see that on the graph. We've got positive slope, we've got negative slope. Right there where it switches, it went from going up to going down, there's a local maximum. If the first derivative changes from negative to positive, well, obviously, that must be a local minimum. We're going down, we stop going down, we start going up. The only way you change from going down to going up is if you reach the bottom and start going back up again. Now keep in mind on both of these, f prime is equal to 0. F prime is equal to 0 right there. But we could also have a situation where f prime is undefined. And still, f prime greater than 0, f prime less than 0. We've still got a local maximum there, and same thing here, f prime less than 0, f prime greater than 0. This is still a local minimum, but f prime again is undefined at that point because we have a corner. All right, what if f prime has no change of sign at C? Well, let's look at a situation like that. This is the one I talked about a little bit earlier. There's f prime equal to 0. There is a critical point right there. But notice that the graph is increasing, and after the critical point, it is increasing, which means that there was no local extrema. And we could do the same thing with a corner, f prime less than 0, f prime less than 0, f prime does not exist because it's a corner. So that's called the first derivative test. And the whole point of the first derivative test, let's just do a quick recap. First derivative test, what do you need to know? Does f prime change sign at some value of x? And I'm going to highlight that because this is something that I want to be able to come back to and think about a little bit later. So let's talk about endpoints very quickly. Endpoints, how do I know if a function is increasing or decreasing? Oh, excuse me, I take that back. How do I know if an endpoint is a local minimum or a local maximum? Well, let's look at x equals a left endpoint. Here's what we say. If f prime is less than 0 for all x greater than a, x greater than a, then f of a is a local maximum. If f prime of x is greater than 0 for x greater than a, then f of a is a local minimum. And again, this may seem very obvious, but this is one of these things in math, we're defining our terms. And once we define them, we don't have to go back and define them later. We can just say, oh, look, derivative less than 0 for x greater than a, boom, that endpoint is a local maximum without having to justify it. Now let's talk about b, which is a right-hand endpoint. And again, if f prime is less than 0 for x less than b, then I have a local max. F of b, forgot to write that. If f prime is greater than 0, wait. Ha! Oops, because I'm doing what I always tell my students not to do. This is f prime greater than 0 because I'm always moving from left to right. And this is f prime less than 0. So if f prime is greater than 0 for x less than b, then I have a local maximum. If f prime is less than 0 for x less than b, then f of b is a local minimum. All right. So let's take a quick look at an example. This will be example 1. And we've got a function, f of x equals x cubed minus 12x minus 5. The first derivative of x equals 3x squared minus 12. I want to know where this is positive or negative, so I'm going to go all the way back to algebra, where what I start is by finding out where it's equal to 0. 3x squared minus 12 equals 0. Adding 12 divided by 3, taking the square root, I get x equals plus or minus 2, which means that at negative 2 and at 2, this function is equal to 0. Now, I'm going to set this up a little bit differently. And I'm going to start by just drawing a number line. And guys, this chart is something that you are going to want to do a lot of throughout this section and continuing, because we are going to analyze the function and the derivative. And the easiest way to analyze it and make sense of it is to just lay it out on a chart. I know that the derivative is equal to 0 there and there. Because the derivative is a parabola, I could plug in numbers and I would figure out whether the derivative was positive or negative. But I know the derivative is a parabola, which means that the graph of the derivative looks like this, which means that the derivative is positive here, negative here, and positive here. I don't have to draw the graph of the derivative, but I visualize the graph of the derivative as a parabola, and I know positive, negative, and positive. So, what does this tell me about the actual graph? Well, what this tells me about the graph of x cubed minus 12x minus 5 is that because my derivative changes from positive to negative, this must be a local maximum. And because my derivative changes from negative to positive, this must be a local minimum. I know the end behavior of a cubic. It goes down like this, it does something in the middle, and it goes up like that. But I also now know that f of negative 2, which equals 11, is a local maximum, and f of positive 2, which equals negative 21, is a local minimum. And knowing that, I can now sketch a graph. Negative 2, 11, positive 2, negative 21, and this is the graph of f of x. And of course, no absolute extrema, because the range of this is infinite. The range is negative infinity to infinity, or we might prefer to drive it this way, which means that there are no absolute extrema, and that tells me that I have a local minimum and a local maximum on this function. Okay, let's do a second quick example. G of x equals x squared minus 3 times e to the x. Notice that the examples are getting more complicated as far as taking the derivative, so you get to practice taking derivatives while doing more advanced calculus. G prime of x equals, we'll call this u, we'll call this v, x squared minus 3, derivative of e to the x is e to the x, plus e to the x times derivative of x squared minus 3 is 2x. I'm going to factor out an e to the x, and I get x squared plus 2x minus 3. Remember, I want to know where the derivative is equal to 0. Well, e to the x is not equal to 0 for any value of x, which means that I'm only interested in when this quadratic is equal to 0. That's a minus. Which means that g prime of x equals 0 when x equals negative 3 or positive 1. Drawing my chart. Again, really, really important. Draw the chart, draw the chart, draw the chart. G of x, g prime of x, it's equal to 0 here and here. Now, you might be thinking, okay, a little trickier on the positives or negatives, but I also know that e to the x is always greater than 0, which means that it does not affect the sign of the derivative, which means that the derivative will be positive when the quadratic is in the positive, and it will be negative when the quadratic is in the negative. So what I now know is that there is a local maximum right here at negative 3 and a local minimum right here at positive 1. Doing some calculations, I discover that g of negative 3 is 6 over e cubed, and g of 1 equals negative 2e. And this is approximately negative 5.5, and this is approximately 1/4. Very approximately. I just did it in my head because it doesn't matter. it's not really relevant. What does this function do at the end behavior? Well, I know that e to the x is going to give me some end behavior that looks like that. We've got a positive times a positive, so we know it's going to be a positive. E to the x goes to 0. We know that both of these go up to infinity. And so what I now know is that my graph is going to look something like local max at -3, local min at -1, excuse me, +1, -5.5, not to scale, and approximate, and then zipping off to infinity. The graph of g of x looks something like that. And you can confirm that on your calculator by just typing it in. But what do we know for sure? There was that little local max right there. There was a little local min right there. Also notice that because our left end behavior says it's going to go to 0 on the positive side, this is an absolute min. And there is no local max, or excuse me, there is no absolute maximum, because my range goes from -5.5-ish up to positive infinity. All right. So why don't you go ahead and do exercise 2 in the book if you are in my class. I'm going to stop this video right here because it's already gone fairly long, and we'll be back with discussion of how to tell whether a graph is concave up or concave down, and the definitions of those. Okay,